A black hole is a region of space-time exhibiting gravitational acceleration so strong that nothing, no particles or even electromagnetic radiation such as light can escape from it. The theory of general relativity predicts that a sufficiently compact mass can deform space-time to form a black hole. The boundary of the region from which no escape is possible is called the event horizon. Although the event horizon has an enormous effect on the fate and circumstances of an object crossing it, no locally detectable features appear to be observed. In many ways, a black hole acts like an ideal black body, as it reflects no light. Moreover, quantum field theory in curved space-time predicts that event horizons emit Hawking radiation, with the same spectrum as a black body of a temperature inversely proportional to its mass. This temperature is on the order of billionths of a Kelvin for black holes of stellar mass, making it essentially impossible to observe one's objects whose gravitational fields are too strong for light to escape. Were first considered in the 18th century by John Michell and Pierre-Simon Laplace. The first modern solution of general relativity that would characterize a black hole was found by Karl Schwarzschild in 1916, although its interpretation as a region of space from which nothing can escape was first published by David Finkelstein in 1958. Black holes were long considered a mathematical curiosity. It was during the 1960s that theoretical work showed they were a generic prediction of general relativity. The discovery of neutron stars by Jocelyn Bell Burnell in 1967 sparked interest in gravitationally collapsed compact objects as a possible astrophysical reality. Once black holes of stellar mass are expected to form when very massive stars collapse at the end of their life cycle. After a black hole has formed, it can continue to grow by absorbing mass from its surroundings. By absorbing other stars and merging with other black holes, supermassive black holes of millions of solar masses may form. There is consensus that supermassive black holes exist in the centers of most galaxies. Once the presence of a black hole can be inferred through its interaction with other matter and with electromagnetic radiation such as visible light. Matter that falls onto a black hole can form an external accretion disk heated by friction, forming some of the brightest objects in the universe. If there are other stars orbiting a black hole, their orbits can be used to determine the black hole's mass and location. Such observations can be used to exclude possible alternatives such as neutron stars. In this way, astronomers have identified numerous stellar black hole candidates in binary systems, and established that the radio source known as Sagittarius A*, at the core of the Milky Way galaxy, contains a supermassive black hole of about 4.3 million solar masses. Once on February 11, 2016, the LIGO collaboration announced the first direct detection of gravitational waves, which also represented the first observation of a black hole merger. As of December 2018, 11 gravitational wave events have been observed that originated from 10 merging black holes, along with one binary neutron star merger. On April 10, 2019, the first ever direct image of a black hole and its vicinity was published, following observations made by the Event Horizon Telescope in 2017 of the supermassive black hole in Messier 87's galactic center. How do black holes form? Primordial black holes are thought to have formed in the early universe, soon after the Big Bang. Stellar black holes form when the center of a very massive star collapses in upon itself. This collapse also causes a supernova, or an exploding star, that blasts part of the star into space. Scientists think supermassive black holes formed at the same time as the galaxy they are in. The size of the supermassive black hole is related to the size and mass of the galaxy it is in. If black holes are black, how do scientists know they are there? A black hole cannot be seen because of the strong gravity that is pulling all of the light into the black hole's center. However, scientists can see the effects of its strong gravity on the stars and gases around it. If a star is orbiting a certain point in space, scientists can study the star's motion to find out if it is orbiting a black hole. When a black hole and a star are orbiting close together, high-energy light is produced. Scientific instruments can see this high-energy light. A black hole's gravity can sometimes be strong enough to pull off the outer gases of the star and grow a disk around itself called the accretion disk. As gas from the accretion disk spirals into the black hole, the gas heats to very high temperatures and releases X-ray light in all directions. NASA telescopes measure the X-ray light. Astronomers use this information to learn more about the properties of a black hole. Could a black hole destroy Earth? Black holes do not wander around the universe, randomly swallowing worlds. They follow the laws of gravity just like other objects in space. The orbit of a black hole would have to be very close to the solar system to affect Earth, which is not likely. If a black hole with the same mass as the Sun were to replace the Sun, Earth would not fall in. The black hole with the same mass as the Sun would keep the same gravity as the Sun. The planets would still orbit the black hole as they orbit the Sun now. Will the Sun ever turn into a black hole? The Sun does not have enough mass to collapse into a black hole. In billions of years, when the Sun is at the end of its life, it will become a red giant star. Then, when it has used the last of its fuel, it will throw off its outer layers and turn into a glowing ring of gas called a planetary nebula. Finally, all that will be left of the Sun is a cooling white dwarf star. Fact time: dying stars create stellar black holes. Say you have a star that's about 20 times more massive than the Sun. Our Sun is going to end its life quietly. When its nuclear fuel burns out, it'll slowly fade into a white dwarf. That's not the case for far more massive stars. When those monsters run out of fuel, gravity will overwhelm the natural pressure the star maintains to keep its shape stable. When the pressure from nuclear reactions collapses, according to the Space Telescope Science Institute, gravity violently overwhelms and collapses the core and other layers are flung into space. This is called a supernova. The remaining core collapses into a singularity, a spot of infinite density and almost no volume. That's another name for a black hole.